video, we discussed about a zero order reaction where rate of reaction was independent of the concentration of reactants. In today's video, we are going to discuss about a first order reaction. Now, first order reaction is the one where rate of reaction depends on one concentration term only. Now let's say if I write one equation like suppose A is forming some products P. So here rate of reaction will be proportional to concentration of reactant to the power 1. If I write 2A gives some product P, here also rate of reaction will be proportional to the concentration of reactant to the power 1. If I have two reactants, suppose A plus B gives some product P. So here also rate of reaction will depend on one concentration term only. Let's see some of the examples of first order reaction. Like we have hydrolysis of methyl acetate. So that is CH3COOCH3. So in this reaction, rate of reaction will depend only on the concentration of CH3COOCH3, that is methyl acetate, to the power 1. Let's take another example, that is inversion of cane sugar, which gives glucose and fructose. So here also rate of reaction will depend on the concentration of C12H22O11, that is cane sugar. Now, let's see how to derive an integrated rate equation for a zero order reaction. So, let's take a reaction. Suppose we have A, it is giving some product B. So, at time t is equals to 0, concentration of reactant, suppose it is A naught, and at that time concentration of product will be 0. Now after some time t, concentration of reactant changed to some concentration, let's say AT. So for this we can write rate of reaction, it will be equal to minus dAT upon dt, and also we can write is equals to K AT to the power 1. Now, solving it, minus dAT by AT is equals to K dt. Now, to get the integrated rate equation, we have to integrate both sides from concentration A naught to AT and from time 0 to time t. So, here we get ln AT, that is log. And I am putting the values ln AT minus ln A naught, and that is equals to KT. Now, I can write it as, I can use the log property log A minus log B, that is equals to log A upon P. So, I am writing it as ln AT upon A naught. Negative sign is there with us, and that is equals to KT. Now, what we can do is, I can write this equation as ln, that is log AT upon A naught is equals to, I can write it as minus KT. In chemistry, we use log base 10. So, I have to convert this to log base 10. So, I will write 2.303 log base 10 AT upon A naught, and that is equals to minus KT. From here, one thing we can do is log AT minus log A naught. I am using the property of log and I am writing it as minus KT upon 2.303. So, from here I can write log AT is equal to log A naught minus KT upon 2.303. Now, Just remember the equation of line. We can write it as y is equal to mx and c. Now, if we plot a graph, I'm plotting graph here. So, if we plot a graph between time and concentration of reactant, the graph will be like this, where the highest point denotes the initial concentration of reactant, while the slope of this line will be equal to minus k upon 2.303. Now, we can write this expression for rate constant, for which we have to calculate the value. So, rate constant K will be equal to 2.303 by T log A naught upon AT. So, this is the formula for rate constant of a first order reaction. And here you can see that if we have to see the unit of rate constant, so we have concentration term, that is A naught by AT. So the units will cancel out each other and only unit for time will be remaining. So unit of K, it will be equal to second inverse, or we can write in simple way as time inverse. So this is how you calculate the integrated rate equation for a first order reaction.